Are you guys ready to proceed in class? Okay, let's go ahead and get started. We'll go to another page, and the first thing we're going to learn is something we've actually done in class. It's called the common ion effect. I'm never sure if it's E or A. I always forget. I think it's E, but it doesn't matter. It's not a test question. Okay. So the common ion effect can be demonstrated with a simple question. So let's just do our example to demonstrate it. So we'll call this example number 1. We're going to calculate the pH of 0.30 molar acetic acid. Now, I'm going to abbreviate acetic acid today as HA to save us some time. I will simply tell you, probably this only time, that acetic acid's formula is HC2H3O2. That is one method of writing it. And the Ka for acetic acid equals 1.8 times 10 to the negative fifth. Remember, the Ka value is the equilibrium constant expression for an acid, in this case acetic acid. So this would be what we would call, this is a chapter 16 problem. This is just an acid in water, just to demonstrate the steps. So step 1 was to read the question and identify the substances which have pH properties. We have acetic acid and, of course, water, which, remember, is always present. Step 2, we look for a strong acid or a strong base. There are none present. Remember the 7 strong acids? And look for hydroxides of the heavier group 2 metals or the group 1 metals. It'll make sense in video when you review. So no hydroxides, no strong acids. So step 2, there's no stoichiometry to worry about. So we go to step 3, which is we find the strongest acid or base, and we focus on its equilibrium. And we make that judgment based upon K values. The higher the K value, the stronger that particular substance is at its job. Here we have an acid with a K value to the roughly negative fifth power, and water whose K value is to the negative 14th, telling us to focus here and ignore this. The contribution from water will be negligible. So we go to the ice technique. As an acid, its equilibrium involves the acid dissociating into a hydrogen ion and the conjugate base. On a test, you may see this. You don't need to write this if you're in class, and if you're on the video, just listen, watching the video, just watch. You may see this in place of the equilibrium I wrote. Remember, they are handled exactly the same. This one just drops water out as a spectator, leaving behind that extra hydrogen ion as part of hydronium. This is a simplified version. It works much more quickly. All right. Since this is equilibrium, we'll use our ice technique. Remember, the I stands for initial, so we will plug in the initial concentrations of the values of the substances present. The initial concentration of the acetic acid is 0.30. And side note, or something I should comment on, when doing equilibrium, the ice technique, we use molarities. We do not use moles. We use molarities because the law of mass action, from which we get the K value, or which we're going to use the K value with, requires molarities for solutions. If these were gases, you may use pressures, if you remember back to that topic, but nevertheless, you have to use molarities for acids and bases. We're not dealing with pressure. Okay, so now I'll continue. The initial concentration of hydrogen is listed as 0. It is not truly 0. Concentration is actually 1 times 10 to the negative 7th from water, but we're going to assume that number is so small, we're going to simplify the process by making it 0. The conjugate base is given a starting value of 0. Now we apply Le Chatelier's principle, or excuse me, more appropriately, we apply the principle of the reaction quotient, Q. We take the initial values and we plug them into the law of mass action, which I'm not going to show, and we get that numeric value and compare it to K, and we decide upon the direction of the shift. Now, because there are no products, we should know that this reaction will shift to the right to establish equilibrium. The purpose of that step is to establish the sign of these changes. Because it shifts to the right, I know that the change in acetic acid to establish equilibrium will be a decrease by some unknown amount proportional to the coefficient, so minus x. Hydrogen's concentration will increase by an unknown amount proportional to its coefficient. Now remember, because these are linked through this balanced equation, the value here, this x value, which was related to the coefficient for acetic acid, can also be related to the hydrogen concentration because they are linked through the balanced chemical equation. In other words, if I say this one decreases by x, this one will increase by x, a 1-to-1 ratio. The same can be true for the conjugate base, which is the acetate ion, which I didn't say earlier. We add down the column 0.30 minus x, 0 plus x is x, 0 plus x is x. We're going to substitute those values into the law of mass action, but before we do, remember, this change, the size of this change is somewhat related to this K value. The K value tells us to what extent this reaction will favor products and or reactants. In a symbolic way, or symbolic representation of the equilibrium expression, by the way, if you're asked to write an equilibrium expression on an exam, this is what they would want you to write, the symbolic version of the law of mass action. So because the K value in this case is much less than 1, it's not less than 0, it's not negative, it's always a positive number, but because it's much less than 1, that tells us that in this fraction here, in this relationship, the numerator is very small relative to the denominator. In other words, this reaction at equilibrium lies far to the left. Or another way of saying it is, when it shifts to the right, it does so to a very small extent. It does not shift very far. Based upon that concept, we can make the assumption that this change relative to 0.3 is so small that we can ignore it. We cannot make that assumption here because it's being compared to 0. Any value is significant relative to 0. So, with that assumption in place, this is greatly simplified. We got x times x on top. On bottom we get 0.30, and that's equal to the Ka value, which 1.8 times 10 to the negative fifth. And so we substitute those values into this expression. We're going to multiply 1.8 times 10 to the negative fifth by 0.3. We'll take the square root, which will give us the hydrogen ion concentration. If you look over here, that's what the x represents. And make a liar out of myself, I actually did not calculate this number. So I'm going to do so real quick. And I get a value of 0.00232 with some rounding. Do you guys who are here in class agree with that number? Okay. Of course, that's with some rounding. Now to find the pH, I'm going to take the negative log of that value. And I'm getting a pH of 2.63. Unless someone in class speaks up, I'm going to assume that's right. So that's just basic pH stuff. Now that doesn't involve the common ion thing I was talking about, nor does it involve buffers. Nevertheless, that's the base principle we're going to repeat ad nauseum, over and over and over and over and over. Okay? Let's move forward to the common ion effect. We can demonstrate the common ion effect with one simple adjustment. So when you review this in video form, compare the question I'm going to say here to the question that we just finished answering. Calculate the pH of a solution composed of 0.30 molar acetic acid, same acid, and 0.30 molar sodium acetate. Now, earlier I gave you the formula for acetic acid. The sodium acetate is a sodium ion combined with the acetate ion, which is the conjugate base of the acetic acid. So I'll show you the formula here. We're going to abbreviate it again just to save a little time. Okay? So notice the only real difference here is that there is an extra chemical, but you have to be cautious here, be careful. That extra chemical we've added is a salt, meaning it's soluble, and part of it has pH properties. Which part of sodium acetate has pH properties? The acetate ion. It is the conjugate base of a weak acid. And we learned in class that the conjugate base of a weak acid is itself a weak base. And we must consider its pH properties. Okay, so let's follow the same sequence. Step 1, identify all substances that have pH properties. We always start with water, obviously the acetic acid, and the acetate ion. There's no need to consider sodium. It is a spectator. Okay? Now, there is no strong acid or strong base present, so no stoichiometry. So then we'll go forward to the equilibrium step, and we will compare K values on the order of to the negative 14th power, to the negative 5th, and for this one. Okay, so we have to use an expression, or excuse me, a relationship that I didn't give you previously. I wanted to wait till now. this is the conjugate base of a weak acid. We are not given the K value for this. It does have a K value, specifically a Kb value, because it's a base. So to determine the Kb value for this, we have two choices. We're either given it outright, which we're not in this case, or we use this relationship, which only holds for a conjugate acid-base pair like acetic acid and acetate. And so, taking that into consideration, or plugging in the values for that, which I'll actually do right now, we're going to rearrange this. We're going to substitute, and we'll rearrange. So there's the Kw value divided by the Ka value. Now, I don't even have to get an answer because I can see that 10 to the negative 14th divided by 10 to the negative 5th is going to be approximately somewhere around 10 to the negative 9th, possibly 10 to the negative 8th. So what? When I determine which of these three to focus on, I judge K values. Whether it's 10 to the negative 8th, 10 to the negative 9th, 10 to the negative 10th, I don't care. Those are all smaller than 10 to the negative 5th. That's the dominant equilibrium. I'm going to focus there. So now it's exactly the same. You've identified the dominant equilibrium compound, and you follow the same technique. Ice, make your assumption that the change is 0 relative to the value, plug in your numbers, and calculate pH. So here, hold on tight, here it goes. Watch for the one difference. Because we're focusing on the acid, I write the equilibrium reaction for an acid in water. I omit the water. I write my ICE. Let me scroll down a little bit for you. The initial concentration of the acetic acid is 0.3. I'm sorry it's off the screen. You'll have to go back and find it. The initial concentration of hydrogen is listed as 0. It's not truly 0, but again, we assume it's so because it's so small relative. 1 times 10 to the negative 7th is small, so we ignore it. Here's where the difference is. The number I put here is 0.3. That's the common ion effect. Okay, so that's the common ion, I should say. Acetate is common here. It's shared by the acid, which has acetate in it, and there is acetate from an external source. Now, according to Le Chatelier's principle, what we would expect is that the presence of this acetate would cause this equilibrium to shift less to the right. In other words, it would reach equilibrium more quickly than if this was not present. And we're going to see that directly because we calculated the pH previously when there was no acetate. So if what I just said was true, if this equilibrium shifts less to the right because there's already a common ion, then the pH at the end should be higher, which would indicate a lower concentration of hydrogen at equilibrium. Okay, so let's see how it works. Here's our initial amounts. We judge the direction of shift. It will shift right again because there is no hydrogen ion. Even though there is a tiny bit, we're going to assume 0. Which defines the changes again. Add down, make the assumption that these are 0 or small relative to the initial amounts. We cannot make that assumption here, and once we make that assumption, we substitute into the law of mass action. Remember, the law of mass action for this acid gives us this Ka. I'll use parentheses to save a little bit of time. There should be brackets. So we're going to substitute in. The concentration of hydrogen is X. The concentration of acetate, 0.30. The concentration of the acetic acid, 0.30. And the Ka value, 1.8 times 10 to the negative 5th. I can see that those two will end up canceling. And the X value, which equals the concentration of hydrogen, is equal to 1.8 times 10 to the negative 5th. You take the negative log of that, and from memory, I believe you get 4.74. Can somebody in class verify that? Okay. Now, notice in the previous problem, the pH was 2.63. Same concentration of acid. Why is the pH higher? Because the presence of the common ion prevented the equilibrium from shifting further to the right, producing less hydrogen in equilibrium, therefore a higher pH. Questions on that? Okay, so I'm going to stop that first video right there.